As dual-degree mechatronics students from Ain-Shams University and the University of East London, and with the support of HCM Lab, we proudly present our graduation project, an autonomous mobile manipulator. In any hospital, the most valuable resource is a medical professional's time. Yet, studies show that nurses can spend up to 40% of their shift on tasks not related to patient care. A huge portion of that time is lost to simple logistics, walking to a pharmacy, searching for equipment, and transporting supplies. Our project directly tackles this problem, an autonomous robotic system designed to handle the logistics. Introducing FlexiBot. The entire system is managed through a secure, web-based command center. Access is restricted to ensure that only authorized personnel can control the robotic fleet. Here, staff can get an immediate overview of the robot's status with real-time data on its operational state and battery life. Here, we can monitor the battery level in real time. The indicator shows green when the battery is at a high capacity. As the robot consumes energy, its status shifts to yellow for moderate and then red for low, signaling that a recharge cycle will soon be necessary. To build the foundation for autonomy, we first create a map. As we manually guide the robot, its LiDAR sensor scans the environment to map walls and obstacles, while the onboard IMU tracks its orientation and movement. We fuse this data together for a highly accurate position and feed it into the G-mapping algorithm. This powerful SLAM technique simultaneously builds the 2D map you see on screen while constantly localizing the robot within it. The final result is this comprehensive map, the essential blueprint that the robot will use for all future autonomous navigation and path planning. Our unique two-part chassis pivots in the center, ensuring all drive wheels maintain traction while effectively climbing over real-world bumps and obstacles. If it encounters an unexpected obstacle, the robot dynamically replans its route in real time, safely navigating around the obstruction to continue its mission. Beyond autonomous navigation, the robot must be able to physically interact with its surroundings. This is the role of its highly versatile, 6 degree of freedom robotic manipulator. Every complex action begins as a plan in a digital environment. Here in the RViz simulator, we can define a precise target position and orientation for the arm's end effector. Once the planned trajectory is confirmed in the simulation, the exact same command is sent to the physical robot. As you can see, the real-world manipulator mirrors the simulation, executing the motion with fluid precision. Each of its 6 joints works in concert, giving it the flexibility to approach a target from virtually any angle. This dexterity is critical for performing complex tasks like pressing elevator buttons or opening doors in a dynamic hospital environment. Upon powering on the control circuit, the manipulator initiates its homing sequence. All motors move in parallel, executing a synchronized trajectory to return the arm to its known default position, ensuring a precise reference point for all future tasks. In an emergency, pushing the stop button cuts motor power and instantly engages electromagnetic brakes on the main joints. This freezes the arm in place, preventing any sudden fall and protecting the hardware. To open the door, we first locate the handle in 3D space using a Connect depth camera. While our vision algorithm identifies the handle, the Connect's depth sensor simultaneously provides the distance. Our robot's physical structure comes together in 3 main stages, beginning with the foundation, the chassis. The central frame, which supports the upper components, is then carefully mounted and fastened onto the chassis, using sturdy aluminum columns. Finally, the storage unit is integrated, locking securely onto the frame with spring locks on both sides for a solid and stable assembly. Storage access is controlled by an authorized RFID card, and the small OLED screen instantly shows whether the door is locked or unlocked. Now, performing a full run. The dashboard provides live monitoring of the robot's status, and from the control page, a user can select a destination on the interactive map and dispatch the robot, seamlessly translating a command into autonomous action. With all systems integrated and a command received from the web interface, the robot is now ready to execute a fully autonomous end-to-end task. It begins by localizing itself on the pre-built map, using a fusion of LiDAR and IMU data to constantly track its position with high accuracy. The robot then plots the most efficient path to its designated goal. As it navigates independently through the facility, its obstacle avoidance system remains active, ensuring it can safely handle the dynamic nature of the environment. Upon reaching the destination, the primary control system transitions from the navigation stack to the manipulation stack. The manipulator arm, which was in its safe, stowed position, now activates. Using its onboard camera and computer vision, it precisely identifies the location and orientation of the door handle, planning a trajectory to interact with it. With a coordinated multi-joint motion, it moves to the handle, grasps it, performs the necessary turn, and pushes the door inward. This successful demonstration showcases the robot's ability to complete a complex mission, seamlessly combining autonomous navigation with precise physical interaction. This sequence represents the ultimate goal of our project, a machine capable of navigating its world and physically interacting with it to complete a meaningful task, entirely on its own. And that is our vision for the future of autonomous systems in healthcare. Thank you very much for watching.